Okay. I'm recording this video just to explain why the exponential function to the power x has this graph. Okay, so let's think about the exponentiation in general. What do we mean by 2 to the power 3? We define it to be 2 times 2 times 2, which is 8. Okay, and what do we mean by 2 to the power n, such that n is a natural number? So 8 to the power n is 2 times 2 times 2 n times. Okay. Okay, so what about 2 to the power 0? 2 to the power 0 is by definition is 1, but why? Okay, we have to for positive integers and the exponentiation, we have two main properties, which is 2 to the power x times 2 to the power y is 2 to the power x plus y, and 2 to the power x, or 2 to the power n over 2 to the power m is 2 to the power n minus m if n is greater than m. Okay, so for example, if you consider 2 to the power 3 over 2 to the power 2. Okay, so in this way, this is 2 times 2 times 2 over 2 times 2. So after cancellation, so you will have 2, which is 2 to the power 1, which is the same as 2 to the power 3 minus 2. You just subtract the exponents. Okay, but this is okay if the exponent of the numerator is greater than the exponent of the denominator. But what about this one? 2 to the power 3 over 2 to the power 3. So with usual calculations, this 2 times 2 times 2 over 2 times 2 times 2, which is 1. So we can just define this to be 2 to the power 0. So if we allow to subtract the equal exponents, so all the time it will be 1, not because this is 1, no, because the usual calculations gives you 1. So we can extend the definition here to the equality. Okay, and the same for the negative powers. What about 2 to the power negative 3? Yes, we will define it to be 2 or to be 1 over 2 cube. So in general, 2 to the power n or negative n is defined to be 1 over 2 to the power n, where n is positive integer, and in this way we define it for the negative because we. Okay, so again, so 2 to the power 2 over 2 to the power 3, by the usual calculations, you will have 2 times 2 over 2 times 2 times 2, which is half. So if you allow to subtract this kind of exponents when the exponent of the numerator is less than the exponent of the denominator, so you will have 2 to the power negative 1. So we are going to define it to be 1 over 2 to the power 1. So and in this way we extend, we don't need this condition anymore, because now we know what do we mean by 2 to the power negative number and 2 to the power 0. Just abbreviation. 2 to the power 0 is just abbreviation for 1. So it means that everything in the numerator is going to be cancelled with everything in the denominator, and something like that, 2 to the power negative 1. So everything in, after cancellation and simplification, you will have 1 over 2. So this is the meaning of 2 to the power negative 1. So now we know what do we mean by 2 to the power n, where 2 to the power x, where x is integer. So now, so let me erase this. Okay, so now we know what do we mean by 2 to the power n, where n is an integer. So let's try to graph it. So at n equals 0, it's 1. At n equal 1, it's 2. At n equal 2, it's 4. At n equal negative 1, it's half. At n equal negative 2, it's 1 over 4, and so on. So this looks like this, but we still have many gaps here. lots of gaps, not many. Okay, so what about, so now we defined the exponential function for where x is an integer. Okay, let's try to extend this definition for the rational numbers. Okay, how? So let's try to ask the same questions. Let's try to ask the same questions that we did for n in n. Okay, so what do we mean by 2 to the power half? Yeah, maybe you say square root of 2. Okay, what do you mean by square root of 2? Just square root of 2 is just an abbreviation or another way to write to the power half. So what do you mean by this one? By this? Yeah, maybe you can think about it as the length of the hypotenuse of this right triangle, or usually we define them to be the solutions of, so this is a number, when we square it we get 2. Okay, so this is x squared equal 2, and the same, 2 to the power 3 over 2, it's the number, when we square it we get 2q. So in general, 2 to the power p over q is the root of this polynomial, which is x to the power u equals 2 to the power b. So now we define those, and it's easy to check this this property, which is let me write it here, that x to the power p over q is less than x to the power r over s if and only if p over q less than r over s. And this will help us to imagine the graph of this, of the exponential function. Okay, let's back to the same to square root of 2. So square root of 2 is defined to be the root of this polynomial, and by the fundamental theorem of algebra, all the time we have this we have the solution, we have this root, it exists, or we define it like that to be exist. So, and actually you studied in calculus 1 many methods to calculate, for example, to calculate the square root of a number or any other radicals. Okay, I think you used to do that using Newton method or Newton-Raphson method or the bisection method to calculate an approximation of them. Okay, actually all what I'm doing now, I'm trying to give you like an intuition why we graph it like that. Where in section I think 6.4 or 6.3 star and 6.4 star, there is a rigorous way which can be, using it we can define the exponential function in an easier way, but this is not the natural one. The natural one comes from the exponents. Okay, so now we can define the exponentiation for a rational number b over q. Okay, and we saw that from this relation that if b over q is less than r over s, so x to the power b over q is less than x to the power r over s. So if you have here, this is half, so it will be less than 1, so it will be something like that here, and all the other numbers. So now we can fill we can fill on many other points which the images of rational these rational numbers. Okay, so now actually in this new z you can see, okay, now we know how to define it over q, over the rational numbers. Q is the set of all rational numbers. Okay, so what about the other numbers which is not in q? We know that the real numbers can be written as rational numbers union the irrational numbers. Irrational numbers, which is the numbers that which are not rational. Here, like many other numbers, many numbers like square root of 2, square root of 3, and so on, and e and pi, and log of n in general, and many points here. And actually, this is uncountable set. Anyway, don't worry about this these properties. These not the ones that we need to define this stuff. Okay, so now let's choose square root of 3. So what do we mean by 2 to the power square root of 3? yeah, actually it's a little bit complicated to define it. So okay, we know that this is a graph where now this is a graph of 2 to the power x, where x in q. Okay, and we want to deal with this function to be something like that. Why to be something like that? We want to fill all these gaps with points such that we get a nice function. So what's a nice function is? A nice function is a big is very wide. So anyway, so a nice function for us is to be a continuous function, is to be increasing function, is to be a differentiable function, as we say. Okay, so actually to do that, so you want to define it to be increasing function. So we want to define, for example, if you choose this point, which is square root of 3, it will lie here, and you want to define it to go with this pattern, to keep the increasing, to save these nice properties. Okay, so how we define it? So actually, let's approximate a square root of 3. So if you could approximate it with rationals, approximate it with rational numbers. If you could approximate it with rational numbers, so maybe we can define it using our magical tool, which is the limit. Okay, let's see how. Okay, let me erase. Okay. Okay. So square root of 3. So you can say that you can approximate this in this way. So square root of 3 is bigger than 1.7 and 1.8. Okay, and then so in this way, so 2 to the power 1.7 is less than 2 to the power 1.8, and I want to define this to be in between, to keep the increasing property. So I will define I want to define it 2 to the power square root of 3 to be in between those. But actually, a square root of 3 is not only between 1.7 and 1.8. Actually, I can go closer. Okay, so for example, maybe you can consider square root of 3 is bigger than. It's not you can consider. Actually, it's bigger than 1.732 and less than 1.733. And again, square root of 3 is bigger than 1.7320 and bigger than and less than 1.7321. And also, square root of 3 is less than 1.73205 and less than 1.73206. Okay, so and this way you can see that 2 to the power 1.732 is less than 2 to the power square root of 3 and 2 to the power 1.733. Okay, let me write. So you'll have 2 to the power 1.7320 is less than 2 to the power square root of 3. We want to define it to keep these properties, to keep these inequalities. Okay, so this is less than 2 to the power 1.7321, and finally 2 to the power 1.73205 less than 2 to the power square root of 3 less than 2 to the power 1.73206. Okay, now let's write them in a good way, such that we can imagine how can we define it. Okay, so now if you look to this part here, so 1.7 and then 1.732, 1.7320. So actually these numbers approaching square root of 3. So because each time I'm going, so let's write it as on the real line. So square root of 3 is somehow here. And then here 1.7, okay, and then here 1.732, 3, 2, and in this way you're approaching square root of 3 from this from the left hand side, okay, from the left. So in this way you're approaching from the left, and here 1.8, and then here 1.733, and so on. Here you're approaching with these values, you're approaching square root of 3 from the right. Okay, and as a values here, you can see that these values, which is 2 power 1.7, and then is less than, actually. So these values here is increasing. So you will have 2 to the power 1.7, 2 to the power 1.732, and so on up to, and I want to have 2 to the power radical 3 is here, and also these powers this is decreasing. This is here is increasing, and here this is decreasing. So you will have 2 to the power 1.8 here, and which is greater than 2 to the power 1.733, and so on. Okay, so let's try to graph this one. So this is square root of 3, and we have these values here. Okay, so the values, if you consider this is 1.7 and this is 1.8, so the values here for this 1.7 and 1.732 comes in this way, moves here up to this point, which we don't know how to define it up to now. Okay, and so the values going in this way, the values 1.7, 1.73, so the values of this, the images of these values going this way, and also 1.8, 1.73, so in this way, when you go in this way, the values going here. So it's somehow, you can think about 2 to the power square root of 3 as a limit. As a limit with what? A limit of 2 to the power somethings. So you can define 2 to the power square root of 3 by using the limit tool to 2 to the power r, where r going to square root of 3 and r is a rational number. So if you have a sequence which is approaching square root of 3 from the left or from the right or whatever, okay, so the values of 2 to the power, these elements in the sequence, is going to use to define 2 to the power square root of 3. So 2 to the power square root of 3, a limit of 2 to the power r, where r approaching square root of 3 and r is rational. Why rational? Because we want to define 2 to the power something which is irrational. So we have to use the rational in the exponent. Because we know how to calculate them. Okay, so now we define 2 to the power square root of 3, which is a little bit complicated to see it. And actually there is one more point. This is not the only sequence which is approaching square root of 3. So if you have a sequence which is approaching square root of 3, and another sequence, a different sequence, yn, which is approaching square root of 3, so the limit of 2 to the power xn as n goes to infinity actually is the same as, we can prove this theorem. So it's the same as the limit of 2 to the power yn as n goes to infinity. So since they are equal, or we can prove this is probable, so this is true, so it's easy to use any sequence. So it's easy, or it's try to define 2 to the power square root of 3 as limit of 2 to the power r as r goes to square root of 3, and this r should be rational numbers. Okay, and in this way we define it. Okay, and we define it to keep the increasing property, to keep the property that these functions will be one-to-one, because if you apply the horizontal line test now, since it's increasing, it will be one-to-one, and actually it will be continuous because it's defined in terms of the limit, so it keeps, we covered all these holes. Okay, So we did all of that just we define it to get this nice function. So now I think I answered the question, and you can see that directly that if you want to graph this 2 to the power x, is going to be increasing. It will have the y-intercept will be 1. When you goes to negative infinity, you will have the x-axis as an asymptote, and here you will have it's unbounded when x goes to infinity. So this is the graph of e to the power x. And also you can imagine if we talk about half to the power x, it will be the other way around. Okay, because actually it's 1 over 2 to the power x. And one more thing, let's me to say it before I'm done. That why we define why you say that a to the power x, why a should be greater than 0. Because actually, consider a equals to a -1 or -2. Okay, so you need to define it over all the to define it over to the power half. So which is the square root of -2, which is not a real number. So this is why we say that a should be positive. And some books say that a should be greater than 1, because just to deal with it easily, because if it's less than 1, it can be written as 1 over something. Okay, you can see that in the book, in page book of Stewart, calculus book, Stewart 8th edition, section 6.2, page 408, 409. Okay, that's it. And using this definition, using the limit, the concept of the limit, we saved our beautiful properties, which is a to the power x times a to the power y is a to the power x plus y, and a to the power x over a to the power y equals a to the power x minus y. So with this definition, we extend the natural definition over positive integers, and we kept our properties, our beautiful properties. Thank you.